Hi everyone, I'm hoping you're all feeling well and safe these days. My name is Ezra, and I'm pleased to present my joint work with my advisor Rothblum here in ITCS 2020. Our paper is called Small Circuits Imply Efficient Arthur-Merlin Protocols, and in one very high-level sentence, it talks about a new connection between circuits lower bounds and protocols that are called Arthur-Merlin protocols. But this is a very high-level description, so I would like to start with a 2-minute abstract that will describe what exactly our paper is about. So 2-minute abstracts, let's get started. So our story begins with two main characters. We have Arthur, which is going to represent a limited resources machine that tries to solve some problem. Arthur must be efficient, but he is allowed to interact with Merlin, which has infinite computational power. And the catch is that Merlin is not trusted, it might be malicious, so Arthur must analyze the information that is provided by Merlin in order to verify that Merlin doesn't try to fool him. Loosely speaking, this is actually the main idea behind Arthur-Merlin protocols. The third character in our story is called the DNF of parties, which is a Boolean circuit that consists of a DNF on the top of the circuits and a layer of party gates, XOR gates below the DNF. And lastly, the fourth character is the binary inner product function. Our paper talks about a connection between these four characters, and specifically, we focus on an open question in circuit complexity that asks whether a DNF of parties can approximate the inner product function. And our results says that a positive answer for this question yields to a very efficient Arthur-Merlin protocols to a wide collection of problems in two models. The first model is called Arthur-Merlin communication complexity model, and the second model is called Arthur-Merlin data streaming model. And the interesting thing in our results is that the resulting protocols are actually, at least from our point of view, they seem to be too good to be true, which immediately leads to two conclusions. The first conclusion says, if we agree that the resulting protocols are indeed too good to be true, then they can serve as an evidence for why the answer for this open question should be negative. The second conclusion says, okay, I don't know if finding Arthur-Merlin lower bound is an easier task, but theoretically, if we find any lower bound on one of our resulting protocols, then I will get the desired lower bound on the DNF of parties for approximating the inner product function. And this is the right place to put some disclaimer. So finding lower bounds in Arthur-Merlin communication complexity or Arthur-Merlin data streaming models is actually considered as a difficult problem. But there is actually lower bound on a slightly different model that is called Arthur-Merlin holographic interactive proof. And the reason I point it out is because in the construction of our protocols, we actually first construct a preliminary protocol in the holographic interactive proof model. And just then, we derive from it a multiple protocols in these two communication complexity and data streaming models. So it might be also an interesting direction to consider and think of. So in a little bit more details, our paper shows that if we assume that there is a polynomial size DNF of parties that computes the inner product function correctly on more than 5/6 fraction of the inputs, then we get very efficient Arthur-Merlin streaming protocols and Arthur-Merlin communication complexity protocols for four kinds of problems. All right, so that was a 2-minute abstract about what our paper is about. And what I want to do now is to explain why we're focusing on approximation. Why we're asking whether a DNF of parties can approximate the inner product function instead of asking whether a DNF of parties can compute exactly the inner product function. And the reason for that is because in the case of exact computation, the question was already been solved and the answer is negative. And actually, we knew that answer already in 1997. So the next question says, okay, we cannot compute the inner product function using a polynomial size DNF of parties, but maybe we can just approximate it. And by approximation, I mean to compute the inner product function correctly only on most inputs rather than all of them. And even that, this question seems to be similar to the previous question of exact computation. We actually don't know the answer in the case of approximation, so currently this question is open. And it's actually a little bit annoying because at first glance, it doesn't clear why lower bounds in the case of approximation is a much more complicated than showing lower bounds in the case of exact computation. But maybe surprisingly, all the non-techniques for secret lower bounds that work in the case of exact computation are started breaking down here in the case of approximation. So intuitively, maybe solving having progress in the case of approximation will give us a better understanding about general circuit lower bounds. And that was also our goal and our motivation behind our work. So in order to be able to talk about the exact quantitatively formal version of our results, we first need to go over some necessary definitions. So let's start with a quick recap about Boolean circuits. So a Boolean circuit is a directed acyclic graph that represents a computation of some certain Boolean function. We have nodes, gates in the circuit, that each one of them computes some elementary function of its ingoing of bits that it gets from its ingoing edges, and then it follows the result by its outgoing edges, where the result or the output of the entire circuit is defined as the output of the circuit at the top of the output of the gate at the top of the circuit. We also have two complexity parameters. We have the depth of the circuit, which is defined as the length or the longest route from an input node to an output node. And we have the size of the circuit, which is defined as the number of nodes, the number of gates in the circuit. We also need to define what are these elementary functions. So we have the AND gate, which takes the N of all its input bits. We have the OR, which takes the whole of all its input bits. We have the NOT, which takes a single input bit and splits its value. And we have a parity gates, a XOR gates, which takes the parity, takes the XOR of all its input bits. So we know what Boolean circuits are. The next step is to define what is a DNF of parities. So DNF of parities is the two circuit with the following structure. In the first layer, we have only XOR, we have only parity gates. And then above it, we have a DNF. So basically we have a layer of parity gates, then a layer of AND gates, and then at the top we have a single OR gate. So we know what is a DNF parities, and what I want to do now is to take a zoom out and to discuss a little bit about what is known and what is unknown about the relation between the Boolean circuits and the end-of product function. So let's start with AC0 circuits, which are constant depth circuits that use only AND or NOT gates. And actually, already from the 80s, we know that with these circuits, we cannot compute or approximate the parity function, which is a special case of the end-of product function. So in particular, we cannot compute or approximate the end-of product function using these circuits. But these circuits don't use parity gates at all. So we have also AC0 with parities, which are again constant depth circuits, but now they have OR and NOT and parity gates. And with these circuits, actually very easy to compute the end-of product function. So let's see an example. So the inner product function is basically takes a product between bits in X and Y, and then we take in the XOR. So the product can be done with a single layer of AND gates, and then the XOR can be done with a single XOR gate. So without parity gates, it is hard to compute the inner product function, but with parity gates, it's very easy. So the next question is, what happens if we allow the use of parity gates, but they can be used only on the very first layer of the circuits? And these circuits called AC0 of parities. And about these circuits, we actually don't know to say a lot about whether we can or cannot compute the inner product function. We do know some weak lower bounds in the general case, or some strong lower bounds in some restricted cases. So for example, we know a strong lower bound when the number of parities is restricted to something like a linear. But we don't know a strong lower bound in the general case. And lastly, we have the DNF of parities with, as I mentioned before, we know that polynomial side DNF of parities cannot compute the inner product function, but we know that result only for exact computation. We don't know what happens in the case of approximation. So what we're going to do in the rest of this talk. First, I'm going to describe our formal quantitative version of our results in the data stream model. And that will, of course, will be right after we will define what are exactly our Arthur-Merlin data streaming protocols. Then we'll do the same but in the communication complexity model. And after that, I will try to give you some technical intuition behind our results. And lastly, in the last part, we discuss about some open problems that are related to our work. So let's start with the data strain model. And in that model, we are going first define what is Arthur-Merlin data strain protocols. And then we'll see the quantitative formal version of our results in that model. So in order to define what are Arthur-Merlin data strain protocols, which are going to be an interactive variant of the traditional strain model, we first need to define what is an interactive proof. So interactive proof is a protocol that between two parties, we have the verifier Arthur, which is limited in resources, and we have the prover Merlin, which has infinite computational power, but it might be malicious. And the protocol proceeds as follows. So the verifier and the prover exchanges some messages, and at the end, the verifier needs to decide whether it accepts the input or rejects the input, where we have two correctness properties. We have the completeness properties, the property that says that if X is in the language, then the verifier accepts with high probability, and the soundness that says that if X is not the language, then no matter what the prover does, the verifier rejects with high probability. And we also have something that is called public coin interactive proof, or also we call it Arthur-Merlin interactive proof. And in that, and in Arthur-Merlin interactive proof, the verifier also have to send to the prover all its random coins and immediately after they were told. So basically, in this type of protocols, we can think about the verifier messages as consisting of only fresh random coins. All right, the next step is to define what is data streaming protocol. So in the traditional data stream model, we have only one party, which is unbound anytime and is required to compute some target function f. We have unlimited time, but we have the following two restrictions. First, we must use only a small amount of space, and in particular, only a sublinear space. Second, we don't have full access to the input. Instead, we get the input as a sequence of bits that is called a stream, and after reading the bit in the sequence, we can no longer read it again, unless, of course, we store it in the memory. So we define what is data streaming model and what are Arthur-Merlin interactive protocols. And what we're going to do now is to combine these two models together. And we'll get Arthur-Merlin data streaming protocol. So Arthur-Merlin data streaming protocol with a parameter K is a protocol that works in two phases. In the first phase, Arthur and Merlin exchange K messages, where the messages that Arthur sends are consisting of only fresh random coins. Then, in the second phase, Arthur gets the input as a stream, and by running a deterministic stream computation, he needs to decide whether to accept the input or reject the input, where again we have the completeness property and the soundness property. And I want to emphasize 2 points about these models. So the first is that I want you to notice that in the second phase, of the protocol is fully deterministic. So basically, during the entire protocol, Arthur is not allowed to have any private coins at all. And the second point I want to emphasize is that Arthur sees the input bits only after the interaction to Merlin, and not before. And the reason I'm emphasizing these 2 points is because there are actually many variants of stream protocols that use some untrusted powerful prover that are different by such kind of settings. All right, so now we can talk about the formal quantitative version of our results in the stream models. So we assume that we have a din of parties that approximate the inner product function to a factor that is greater than 5/6, and we get efficient Arthur-Merlin data stream protocols for 2 kinds of problems. The first one is actually all the problems that are computable by low-degree polynomials, and the second is a concrete problem that's called the party triangles problem. But first things first, so let's start with the first problem. So our first result says that if we have the of a polynomial size DNF of parties that computes the inner product function to a factor that is greater than 5/6, that approximates the inner product function to a factor that is greater than 5/6, then we get an Arthur-Merlin data stream protocol with d rounds of interactions for every Boolean polynomial with total degree d. where the proof length and the space complexity are quasi-linear with the total degree D, and logarithmic with n, where n is the number of input bits that the polynomial gets. So these are our first results. And just to give you some quantitatively intuition about the efficiency of this protocol, I want to consider, for an example, the case that the degree D is a constant. So if D is constant, we get here a constant round, a protocol with a constant number of rounds, and a proof and space complexity that is logarithmic with 10. However, if we will use the famous sum check protocol, then we'll get again a constant number of rounds, but the complexity is going to be something like n to the factor of 1 divided by n. So by simply assuming that we have a polynomial size d of parity that approximates the inner product function, we get an exponential improvement to the famous sum check protocol. So that was our first results. Our second result is in a problem that is called the parity triangles problem. And the parity triangles problem, we have a graph which is vertices are all the numbers between 1 and n. And the input to this problem is actually the edges of the graph. And the goal is to count the parity of the number of triangles in the graph. So our result in the parity triangles problem is that, again, we assume that we have polynomial size d of parity that approximates the inner product function, and we get a Arthur-Merlin data streaming protocol for the parity triangles problem, where the number of rounds is only 1, and the proof length and the space complexity are polylogarithmic to 10, where n is the number of vertices in our graph. So that was our results in the data streaming model. And now I want to discuss about our result in communication complexity model, and I'm going to skip about the formal definition of what is Arthur-Merlin communication complexity. So you guys can think about it as basically taking a standard communication complexity model, but the parties first run a public coin interaction with some untrusted powerful prover, and just then running a standard communication complexity protocol. So let's go to our results in that model. So in the communication complexity model, we construct two protocols, one for low degree polynomials and one for all the languages that are decidable by constant depth circuits. So let's see the first result. So again, we assume we have the NF of parity that approximate the inner product function to a factor that is greater than 5 over 6. And we get Arthur-Merlin communication complexity protocol with one round of interaction, where the communication complexity is logarithmic with the number of monomials of the polynomial. And if we take, for example, a polynomial with a total degree d, then the communication complexity becomes to d times log n, where d is the degree of the polynomial, and n is the number of bits the polynomial gets. And I want you to notice that in construct to the protocol for polynomials that we got in the streaming model, which had d rounds of interaction, here we only have a single round of interaction. And actually, it is very useful because it lets us extend our results to a protocols that also can decide any language that is decidable by constant depth circuits. And we do it by using a non-technical Rothblum that convert constant depth circuits to polylogarithmic degree polynomials. And then we basically use these results. So by using Rothblum techniques, we get our fourth results, which says that if we have small d of parity that approximates the inner product function, then we also have Arthur-Merlin communication complexity protocol with one round interaction for every language that is decidable by constant depth circuits, where the communication complexity is polylogarithmic with the size of the AC0 of the constant depth circuit. All right, so that was our results. And in the few minutes that we have left, I want to give some basic intuition about the constructions of our protocols. So we have 4 kinds of protocols in our work. And actually, all these 4 protocols are based on some preliminary protocol which we build first, and then from it we construct or we derive all our four protocols. And the preliminary protocol is going to be a protocol of a special type of interactive proof system that is called holographic interactive proof. So holographic interactive proofs are basically very similar to interactive proofs, except that the verifier doesn't have direct access to the input. Instead, you have an oracle access to an encoding of the input via some linear code. So we also have a new complexity parameter, which is called the query complexity, which is the number of queries the verifier makes to the linear encoding of the input. And we have a new denotation. So by AM AJP, we define the Arthur-Merlin or the public coin version of holographic interactive proof, where K indicates the number of messages that are exchanged during the protocol. So the flow of the construction of our protocols actually goes as follows. We start with some assumption about DNF of parties that can approximate the inner product function. And in the first step, we construct a one-round Arthur-Merlin holographic protocol that verifies inner product lines. And this part is actually the only part in our work that directly uses the assumption about the DNF of parties. All our other four protocols are actually going to be built from the holographic protocol, and thus they use the assumption about the DNF of parties only implicitly. So I kind of lied before when I said we have 4 kinds of protocols, because we actually have 5 kinds of protocols. And I want to focus on the protocol for the holographic protocol for inner product lines, because this is the part in our work that connects between Boolean circuits and interactive protocols. So what we are going to do now, I'm going to give you some intuition of how to construct holographic interactive proof for inner product lines with one round of interaction from the assumption that we have small DNF parties that approximate the inner product function. So first, let's see the formal lemma. So the formal lemma says that if we have polynomial size DNF parties that approximate the inner product function to a factor that is greater than 5 over 6, then we get a one round Arthur-Merlin holographic interactive proof with logarithmic queries and proof length that can verify any inner product line. And since we're going to construct an holographic interactive proof, I also need to tell you which linear code our holographic verifier is going to make its queries. So the linear code we are going to use is actually the output of the party layer of the DNF of parties that we assume that exist. So the first layer, the party layer of DNF of parties, is actually consisting of only XOR gates. So its output bits can be considered of some linear combination of the input bits. So we can think about it, the output bits of the party layer, as some part of some encoding of the input bits via some linear code. So our holographic verifier is going to make queries to the output bits of the party layer of the DNF parties that we assume that exist. All right, so let's build our protocol. And as a warm-up, I'm actually going to build a protocol that doesn't work, but it will give us a good intuition for how the actual protocol is going to work, and also going to help us to build later the actual working protocol. So we assume that we have a small DNF parties that computes the inner product function correctly on most inputs. So the prover can simply set an index of a certified clause, a certified AND gate in the circuits, and the verification can be done by simply reading the entire circuit, the entire clause, and checking that is indeed satisfied. So the proof length is good. The proof length is logarithmic in the size of the circuit, so we like it. But the query complexity might be large, because the query complexity is equal to the size of the clauses, and no one can promise me that the clauses is not very large. And we also have another problem, and is that our protocols only works on the average case, because we start with a circuits that can compute the inner product function correctly only on most inputs. So we get a protocol that can verify only inner product lines on most of the inputs, but not all of them. And moreover, our protocol can only verify whether an inner product is equal to 1, but it cannot verify whether an inner product is equal to 0. So we have these two problems in our protocol, and we want to fix them. So let's start with query complexity. What we are going to do is we are going to reduce the query complexity by making some pre-processing on the circuit. And in that pre-processing, we're going first to remove all the white clauses in the circuit. And then after we remove all the white clauses, we are going to run that protocol. And because the circuits will no longer have a big clauses, the query complexity is become too small, become too logarithmic. So let's see it. So since each clause is an end of output bits of the parity layer, then each clause is actually a system of linear equation of the inputs. So before we're removing the white clauses, we're actually going to first eliminate linear dependencies within each clause. And only then we are going to remove white clauses. So by making these two modifications, by definition, we get a circuit with only logarithmic size clauses. So if we run the protocol that we saw in the previous slides, we'll get a protocol with query complexity that is only logarithmic, which is as required. But as you might suggest, or might guess, these two modifications also introduce some error. The good thing is that they introduced only a small amount of error, and that is because we removed only white clauses, and each one of these clauses actually defines a set of many independent linear equations. So each clause removed actually adds only a 2 to the factor of minus 100 log s error to the circuits. So by taking the union bound, we actually add only a 2 to the factor minus 100 error to the circuit. So we only add a small error to the circuit. Okay, so what we achieved so far, we achieve a protocol that has the required complexities, but it works only on the average case, and it can only verify whether an inner product is 1. It cannot verify whether an inner product is 0. So we want to convert this protocol to a protocol that can verify any inner product lines. And the first idea is to use something that is called, that we refer to as the self-correction property of the inner product function. So since the inner product function is a linear in each one of the texts, we can actually get the following identity, where note that if we take V and U as random, then the terms in the right-hand side of this identity are correlated random inner product values. And that's great, because we have a protocol that works in the average case. So we can, instead of asking the prover what the value of the original inner product line, we can ask the prover for the values that in the right-hand side of this identity. We can verify them with high probability in our average case protocol. And then we take the XOR of the results and get the results of the original inner product line. So it seems promising, but the problem is that it still doesn't work. And that is because our average case protocol can only verify whether an inner product is 1. It cannot verify whether an inner product is equal to 0. So if the prover tells us that one of these terms is 0, our verifier can't verify it. So we still want to use the self-correction property, but we want to find a way to detect also when the prover sends a false 0 line. When the prover says that something is equal to 0, when actually equal to 1. And the way we are going to do it is by the following two observations. First, I want you to note that the expectation of the real values of these random correlated terms is the expectation of the inner product function, which is roughly an half. The second observation is that since we can verify with high probability all the inner products that are claims to be 1, then if Merlin lies with high probability, he must lie only by saying that some term here is 0 and actually 1, but it cannot do the opposite because we have protocol that can verify it with high probability. So basically, if the proof lies, then the average value of its claims is reduced compared to the real values. So the average value of the prover claims is actually different when the prover lies and when he is honest. That means that we have some statistical gap between the cases, and we actually can detect it by simply running the protocol multiple times, each time with a different random with a different randomness. We are going to verify only the claims only the terms that the prover claims to be 1, and we're going to blindly accept all the terms that the prover is going to say us that they are equal to 0. But at the end of the protocol, we're going to check that if the average value of all the claims that the prover sent to me are either close enough to the average value of the inner product function, or of the expectation of the inner product function. So this is the high-level outline of the construction of our holographic protocol for inner product lines. From now on is actually only some technical statistical analysis, so I'm going to skip it. All right, so now we reach to the last part of our talk, and in this part we're going to discuss a little bit about some open problems that are related to our work. So the first problem is actually the annoying 5/6 limitation over the approximation of the DNF of parties. So I remind you, all our protocols are constructed by the assumption that we have a DNF of parties that computes the inner product function correctly on more than 5/6 fraction of the inputs. And the 5/6 actually came from the use of what we call as the self-coercion property of the inner product function. So an interesting thing to do is to study whether and how we can push this constant, this 5/6 fraction, to something that is called to the conjecture half plus epsilon approximation. Also, the second direction, it might be interesting to be able to construct protocols for zero circuits also in the strained model. So currently we know how to construct protocols for zero circuits, efficient protocols for AC0 circuits, only in the communication complexity model. So it might be interesting to do the same also in the strained model. Also, it might be powerful if we find a way to construct efficient protocols for the NC1 class, whatever it is in the data strain model or in the communication complexity model, or even in the holographic interactive proof model. And the reason that it might be interesting is because there are actually lower bounds, Arthur-Merlin lower bounds for NC1 problem. And lastly, of course, we have the golden goal, which is showing circuits lower bound, showing that the NF parties cannot, or maybe can, I don't know, approximate the inner product function. So thank you for listening. That was our paper, Small Circuits Imply Efficient Arthur-Merlin Protocols.